Hello! So, in this video, I'm going to do really just a quick informal, maybe not that quick, informal introduction to just mathematical test theorems. I'm putting these in quotes here, in general. So, in particular, we're about to launch into a whole bunch of videos, all regarding different forms of testing for convergence of series. But these sort of testing for something, if what you're working with has these properties, then this other feature holds. These are ubiquitous in mathematics. They're used for all kinds of things, right? So in our case, like I said, we're going to be talking about, if you have these hypotheses, then you know that maybe the series converges or the series diverges or whatever, okay? But this is true in all kinds of things, right? And you've seen this already a bunch. Like if this sequence has these features, like if it's increasing and bounded above, then it converges, right? So that's a convergence for sequence. If you have this property about for every epsilon, there's a delta, such that if you choose x close enough to some point, within delta of that point, then you can show that it's within the image is within epsilon of the image of that point, right? That's the whole continuity thing. Sort of set out very vaguely, but still. So you have these sort of if-then statements, right? So these test theorems, if this, then that kind of theorems, it's important to sort of understand how to understand these theorems, how they're structured, and sort of what to do with them. Typically, in mathematics, especially most of your math coming up until you hit sort of real hard proof-based classes, a lot of the times we just told you like this is a fact, and then we just sort of freely apply the fact. Like you can invert, you can do commutativity for addition, and then we do that to do some stuff, right? But now that we're at this point in math, and I promise I'll start writing stuff in a second, but now that we're at this part in math, it's sort of important to know when stuff works, when it doesn't, and what it means even to work versus not to work, okay? So let me give an example. Actually, let me use a different color. So let me give an example as a way to start, and then I'll talk about these things sort of in general. So we've already done, as a convergence test, the test for divergence. And we mentioned the most common way to apply this is the contrapositive, so I'm just going to write that directly, which is that if an does not go to 0, is the shorthand, right? The limit as n goes to infinity if an is not 0, then the series an for n going from wherever it starts to infinity diverges, or does not converge, whichever way you want to write it, okay? So it's an if and a then. So you would sort of think that there's there's sort of two possibilities. Either it works or it doesn't. And that's sort of true, but sort of not. So I would classify, and I admit this is sort of my own pedagogical thing, this is not a standard math thing. If you ask another math teacher the phrasing or what to use, they'll look at you funny. But there's really three sorts of situations that you want to separate a test into, okay? So I'll write these down in yet another color to keep track of this. So the first thing you want to ask yourself is, does this test have a positive and or negative result? I'll call it a success. I'm putting these in quotes because I'm going to explain what I mean by these terms, okay? So this is one example. Another example we did was the geometric series. We had a theorem for geometric series that said that if you have the series a times r to the n going from some k to infinity, then this series, this converges. I'm sort of writing this a little weirdly, but so this converges if r is less than 1, and this diverges if r is greater than or equal to 1. Okay. So this is a good way of showing what I mean when I say positive and negative success. So which way is positive and which way is negative is really a matter of reference frame, point of view. But what I mean by that is that there are sort of two opposite outcomes. So in this case, I could say the positive success is this idea that I have a converging thing, right? Under some set of conditions, I can show that it converges as a positive success. Under some circumstances, I can show that it diverges, which I might consider a negative success. This thing fails to converge, okay? As opposed to, this is the second possibility / thing to think about, can this theorem fail? And this is why I make a difference, I draw a difference between positive negative success as opposed to fail. Because here, if I know that r is less than 1, I know something, I know it converges. If r is greater than or equal to 1, I know something, I know it diverges, right? Often people will think that the test failed because it diverges, meaning that it failed to converge. But that's not a failure of the test, it's a failure of convergence for the series, right? The test succeeded in the sense that it gave you an outcome you know, not the one you hoped for, so it might be negative, but it gave you an outcome. As opposed to the test for divergence, where if an doesn't go to 0, well then I know something, I know this diverges, which again, depending on your point of view, maybe you would say that's positive because it's a test for divergence, you did show it diverged, or negative because you don't want it to diverge, but regardless, you succeeded in the sense that you have information. But this test for divergence can fail because if an does not go to 0, that is a failure of the test. I know nothing more than I did before, okay? That's the difference. Here, regardless of what r is, I know stuff, right? If it's bigger than or equal to 1, I know something. If it's less than 1, I know something. It succeeds either way, it just gives me a different answer. Up here, I only know stuff if it doesn't go to 0. If it does go to 0, the theorem itself just fails, okay? That's the real sort of core difference, is that the theorem, when it fails, the theorem doesn't give you anything at all, okay? And so this sort of leads us to the third thing, which is what do I need for the theorem to succeed? Yeah, I didn't spell that right, but that's why I'm a math major, not a English. All right, so on the first thing you say, okay, do I have positive and or negative successes? Really what you want to ask yourself is, do I have more than one possible outcome that I know for certain what the outcome is? Here, I know it could converge or I know it could diverge, whereas up here, I only have the one possible outcome. I only know that it might diverge, right? The second one says, okay, is it possible that you could try to apply this thing and not get any information, right? And in some sense, that's always possible, in the sense that really what it's asking is, can you have a situation where you don't satisfy the hypotheses? Typically, you don't encounter that with a geometric series because you don't think to use the geometric series theorem until you have actually identified that it's a geometric series in the first place, right? So the fact that it's a geometric series is sort of the catalyst to even invoke this theorem. Whereas the test for divergence, it may not be obvious looking at it what the limit of the nth term, right, the limit of the an is, so you might invoke that thing before you find out that it really does go to 0 and thus it failed, right? But really it comes down to, is it likely or plausible that you will not actually apply the hypothesis correctly, and what does that mean? And sort of more importantly then, this third thing is saying, what then, thinking about what you just figured out from part 1 and part 2, the third one is saying, what do you actually need to know in order to get some information from using this tool, right? So for tests for divergence, you absolutely need to know that the limit goes to zero. That the limit doesn't go to zero, right? If the limit does go to zero, you don't know anything. So that's what it means to get any information out of using that theorem. Likewise, the geometric series, as long as it is a geometric series, you will succeed, right? So really, what do I need to know for the theorem to succeed is that you have a geometric series. At that point, you're good, okay? There's no other sort of pitfall to run into. This sort of culminates nicely, such as it is. I say nicely in that we will see some theorems. So I'm going to write a theorem I haven't introduced as of this video, but we will see later on. So this is Cauchy's ratio test. So this theorem says that if you have some series an for n going from some start point to infinity, and you know if the limit as n goes to infinity of a n plus 1 over a n is less than 1, then this series, I'm just going to shorthand it as that thing, converges. If the limit as n goes to infinity, that's a terrible n, sorry, as n goes to infinity of a n plus 1 over a n is greater than 1, then the series diverges. Again, I'm shorthanding this, and I will rigorously go through this when we get to that point in the videos. And this is why, so I'm going to point out why it is so important to sort of actively think about this. So here, do I have positive and or negatives? Well, I have both, right? I have a situation where I get convergence. I have a situation where I have divergence. I have more than one possible result, right? Which one I label as positive or negative, it doesn't really matter. The point is that I have more than one possible outcome. Can this theorem fail? So this is the sort of key part, that unless you're actively thinking about this, it won't necessarily jump out at you. Because what hasn't been written here, because from a mathematical standpoint, it is inherently written, right? It's implicitly written by the fact that it wasn't written, which is why this is weird. But if you look at this carefully, what I haven't said anything about is what happens when the limit equals 1. And that's because if it equals 1, we don't know anything. So there's nothing to write there, right? I don't know it converges, I don't know it diverges. And so can this theorem fail? Yes, it can fail. And in fact, if I get that the limit equals 1, it has failed in the sense that it tells me nothing. There's no information gathered by using this ratio test, okay? So not only can I have more than one outcome where I do know stuff, but I can also simultaneously have a failure outcome where it tells me nothing, right? And so what do I need to know for this theorem to succeed? What do I need to know for this theorem to give me information for this test or criterion to work? Well, I need to be able to take this ratio and get something that is effectively not 1, right? So if I can get that this limit of this, the an plus 1 over an, and there's some more stuff I didn't actually write carefully because again, we haven't covered this yet. But if I get this thing and it doesn't give me 1, if it gives me something smaller than 1 or bigger than 1, well, then I know, right? Then I know I got something. It tells me something definitive. Likewise, if it gives me 1, then I know that it didn't tell me anything, and so that test was a waste of time, okay? So the thing I'm trying to hammer home here is that with all of these mathematical tests, it's important to understand the difference between getting a result definitively that is not a result you wanted, right? Like this series diverges when you were hoping it converged, versus going through a bunch of work and discovering that all that work was a waste of time because you got something that is fundamentally not information. It didn't give you anything. Like if you take the ratio of these things, you go through a bunch of work to try to finally figure out what that limit is, which can be really gross and annoying at times. You find the number, crunch it all the way down, you get an answer, and you get 1. Unfortunately, that means you really did just waste your time. It didn't tell you anything. Now I put an asterisk on that because the fact that it didn't tell you anything, the test, might tell you something as a mathematician. For example, if the ratio test fails, then the root test will probably fail. But from a test standpoint, from the theorem itself, the theorem does not give you any conclusive proof, any conclusive result. That's the thing you want to really understand, okay? And I will say the last thing that you should do, which is sort of different from these, so I'm going to write it in a different color, but the last thing you should do is come up with an example for every possibility. So for example, for the ratio test, right? The ratio test so maybe I would do something like the series, let's say 2n over 3n plus 1. So all of that, there we go, to the n equals 4 to infinity. So this is a good example of a situation where if I did the ratio test and I did it out and I finally got an answer, I could actually show that this thing converges, because this as a ratio will end up going to something like 2/3. So this would be converge, versus I could come up with another example, something like n equals 2 to infinity, and you don't have to do something that's convoluted, I just made that up off the top of my head. You could do something like, let's say, n factorial over, let's do n, would be a good thing to put there. Let's just do n minus 1, why not? So you could do something like this. And this would be something that if you did it through the ratio test, you would get spectacularly, in fact, that this thing diverges. In fact, the ratio test is a little overkill for that. And last but not least, an example for the other one might be something like n equals 3 to infinity of, let's say, 1 over n plus 6. And this one would be where the ratio test, as a ratio test, fails. Okay? And the point of coming up with these examples is A, to make sure you understand sort of what it means to succeed or not, right? If you can't come up with examples, then you probably don't understand the things you should understand up here. But also, coming up with examples helps you understand the sorts of settings where a test is more likely to be helpful than others. For example, polynomials like n plus 6 behave badly with the ratio test. So if all you have is polynomials in the top and bottom, probably you're not going to want to use the ratio test. So as opposed to something that is sort of pseudo-geometric like this, it does work really well with the ratio test. Usually, not always, but usually. So these are the sort of situations where you can get it to work a little bit better, right? That you can, by coming up with examples, you sort of build an intuition as to when to use one test over the other, okay? So this video is a little longer than I wanted it to be. I might cut it down in editing, which might be really confusing. So if you see me sort of teleport around and start and stop mid-sentence, it's because I decided I didn't want to bore you with stuff and cut it out of the video. But since really the rest of what we're going to be doing in series after this point is really generating, proving, and using tests of various forms, this idea is very important to understand because it's basically going to be taking over all of the rest of this section. So this is sort of a nice way of internalizing each of the tests that we're going to start coming up with. Okay? And that is that. That is that.